Hi there, I'm Robin, and this is the recording for Stat 776 Lecture 4, which is on Popan models. Um, and I should say that we're going to split this lecture up into smaller chunks. So this is the first one. I'm going to be giving the next two lectures. This one on Popan models, which are models for estimating population size and demographics from capture-recapture studies in open populations. So this lecture will be pretty theoretical. And then the next lecture will be on Kapow, which is a web application for capture-recapture power analysis using Popan models. This is really why I'm here. I've been working over the summer with my supervisors on updating Kapow, which was already has been around for a few years, but needed some more development. And we've got it to a place that we're excited about trying to see how people do with it. So we thought it would be a good opportunity to use it in this class to help you guys understand Popan models and also to see what your experience of using it is like. So that'll be next week's lecture, and that'll be much more applied. The reference material for these two lectures will be a brief survey of capture-recapture, which are notes that Rachel, my supervisor, wrote. Really excellent notes, easy to read and interesting. Pages 1 to 5 and 17 to 24 will be relevant, especially 21 to 24. And I can quickly just show you those. Yeah. So pages 1 to 5 will be a really good review just of capture-recapture in general and closed population capture-recapture, which is actually mostly what I'm going to cover in this very first section of lecture 4. And then pages 21 to 24 are the ones specifically about Popan models. So, and introducing Kapow as it existed a few years ago. And as well as those notes, I've written a data exploration of some open population capture-recapture data for Maui dolphins. So we'll probably get into that next in the next section of this lecture. I can show you what they look like as well. All right, so it's an R Markdown document, so I'll provide that and you can go through and have a play with the code if you like. And I'll also have it knitted to a, if I can show that. I'll also have it knitted to a PDF if you maybe don't have RStudio or just would rather just read it in PDF form. Okay, so there's my email there, and I'd love to get any questions or feedback by email. This is my first time giving a lecture in statistics, so I'm pretty excited about it. And I should say thanks to James for giving me this opportunity. And also thanks to my supervisors, Rachel Fuster in statistics and Emma Carroll in biology, who taught me everything I know about this. Okay, so Popan models are models for capture-recapture studies in open populations. So an open population means that it can change during the study. So animals can be born and die and migrate. So it's quite a lot more complex than closed populations. So what I want to do in this first section is review closed populations and try to get really clear and solid about how capture-recapture works for closed populations. So capture-recapture is performing multiple surveys at intervals that are long enough for mixing so that you're not always catching the same animals, but where the intervals are short enough that, well, I should say, so just capture-recapture in general is just doing these multiple surveys. The capture histories are based on multiple survey tags or re-identification of animals. So you will have a capture history for every animal that you see, and the way you can do that is either by giving them different tags for each survey, or you could give them an ID tag so that you could know when you recapture the same animal and when you don't capture it. And you can also identify animals with photos or DNA or other methods. So that's an area of development. And then you use the patterns of captures of the observed animals to estimate the number of unobserved animals using statistical magic. Right? So it's pretty amazing that from the animals that you do see, you can actually figure out how many you didn't see. So that's really the cool part of capture-recapture. And so closed population capture-recapture is where you assume that the population doesn't change during the study. So your study duration has to be short versus the generational time of the animals. So it depends on the animals. If the animals live a very long time and reproduce slowly, you could have a study over years and assume that the population hasn't changed very much. But otherwise, for shorter generational times, you'll need shorter study duration. The parameters are the population size n and capture probabilities p. And the way that capture probabilities are specified depends on the model that we're using. So let's look at some closed population capture-recapture data and review what it means. Okay, so this is the code that you've seen already from James's lecture, lecture 2. Unfortunately, I missed that lecture, but I've read through the notes. So I'm sure I'll be repeating a little bit here, but I think it's good just to be really clear on closed populations before we move on. These notes are actually what Rachel gave me when I first started learning about these models. So let's just source the code and we'll simulate this first population of animals and the capture-recapture data. So let's have a look at the first few rows. So each row represents one animal and each column represents one survey. So there are 5 surveys here. And it looks like most of the time, well, all of the time for the first few animals, they're only being caught once each. So they're not being caught in most of the surveys. Now we can check the minimum number of times that any animal was captured. And of course, the minimum is 1, because if there were any animals that were not captured at all, we would not have them in our data set, right? Now we can look at the number of animals captured in each survey, and that's the sum of each column. So we can look at that. Okay, so between 40 and 121 animals captured in each survey. And we can also look at the total number of animals captured by looking at the number of rows of the data. So in total, there were 331 animals captured. So each survey, none of the surveys actually caught more than half of just the animals that we saw. So that would seem to suggest that we're not getting close to capturing all of the animals. So there's probably quite a lot more animals out there that were never caught at all. And that's true. The parameters that we estimated, that we simulated the population with, or simulated the data with, were a population of size 1,000. So quite a lot more than the 331 that were ever caught during the study. And the capture probabilities were this vector here. So different capture probabilities for each survey, which is model MT, right? So the capture probabilities are changing over time. And as we thought, they are all quite small. They're all below 0.5, although that can be totally realistic depending on the study. So let's simulate another population and have a look. I should say we're simulating both the population and the capture histories. So again, we're doing 5 surveys, but this time most animals are being caught most of the time. And we can have a look at how many are caught in each survey. And there are a lot more caught in each survey than in the last simulation. So you might think that the population must be a lot higher. Now let's have a look at how many are caught altogether. And well, it's more than last time, but it's not much more than the largest number caught in just one survey. And actually, in all of the surveys, we're catching almost half or much more than half of all the animals we ever see. So we might think that we're getting pretty close to capturing all of the animals over the survey. And actually, that's exactly right. The population size that we use to simulate the data is 500. So we actually caught every single animal at least once. And the reason is that the capture probabilities are really high. And so 5 surveys with high capture probabilities means it's not surprising that we caught every animal. I'm not sure if this is ever very realistic, but I guess it just depends on the study. So these ideas about comparing the numbers of animals that you see in any particular survey with the number that are caught altogether means these ideas are how Model MT works. So we use statistical theory to express those ideas precisely. And then what we end up with is this model. Let's just see how it works for this second set of simulated data. So I'm just rounding the results of fitting Model MT to the second set of data. I'm just rounding them to 3 decimal places, so it's easier to read. And if you compare the capture probabilities here with the true values here, you can see that they're very close. And wow, the estimate for n is exactly the true value of n. And also the confidence intervals are tiny. So the model has fitted very, very well to this second data set. And the reason is that the capture probabilities are so high. So when you're capturing almost all of the animals on every survey, you're going to have a very good chance of figuring out exactly how many animals there are. So let's try fitting Model MT to the first data set again. Again, because you've done it before. And compare the true capture probabilities with the estimated ones. Oh, they're pretty close. This one's a wee bit off, but in general pretty close. And actually the estimate for n here is not too good, and the true value of n is actually outside of the confidence interval. So it looks like the simulation for this population was especially bad this time. We probably didn't capture that many animals. And so that's what can happen sometimes. But in general, this scenario with quite low capture probabilities and not a very, very high population means that in general, this will be quite a difficult scenario for model MT. Okay, so that's closed population capture-recapture data and fitting model MT. Let's have a look at how model MT actually works. Okay, so the closed population models that we're studying use maximum likelihood estimation. So we're estimating the parameter values with those that give the highest probability of the observed data. So the probability of the data for any values of the parameters is called the likelihood. And so that's what we're maximizing to get our estimates. And for this kind of closed population capture-recapture data, the probability of the data can be written in terms of the binomial distribution or the multinomial distribution. Probably everybody has seen the binomial distribution, but the multinomial is a more complicated extension of it, and you might not have actually seen this one yet. So let's review it. So starting with the binomial coefficients, these are usually presented as the number of ways of choosing X objects out of N. But you can also think of it as the number of ways of dividing N objects into two groups, one with size X and one with size N minus X. It's just a different way of saying this. But if you think of it this way, and this might be pretty obvious, but if you think of it this way, then the multinomial will be a lot easier to understand. So the notation is this choose function notation, the number of ways of choosing X elements out of N. And this is the definition in terms of factorials. So N factorial is the number of ways of ordering the N objects. So you could have any of the N objects in the first place, and then you would have N minus 1 that you could choose for the second place, and N minus 2 for the third place, and so on. And if you multiply all those possibilities, you get N factorial. And then if you have all of the ways of ordering N objects, and you choose the first X to assign to one group, and the last N minus X to assign to the other, if you do that for all of the orderings, you'll actually have every possible way of dividing up those objects. But you'll also have every possible ordering of each of those groups for all of those ways of dividing the objects up. So you actually need to divide by the number of ways of ordering each of the two groups, which are just X factorial and N minus X factorial. And so when you divide the N factorial by the X factorial and N minus X factorial, that gives you the number of ways of dividing up N objects into X and N minus X without including all the different orderings. Okay, so the binomial distribution is usually presented as the probability of X successes in N independent trials when each has a success probability of P. But you can also understand it as the probability of dividing N objects into two groups with sizes X and N minus X, given that all of the classifications are independent with probabilities p and 1 minus p corresponding to the second group. And this way of understanding it extends to the multinomial a lot easier. And this is the expression for the probability for any value of x given your parameters n and p. So you've got the number of ways of dividing the n objects into the two groups. And then this is the probability for each of those ways of dividing them up. So because the classifications are independent, you're just multiplying the corresponding probability by the number of objects that are being classified with that probability. So if x are going into the first group, which has a probability of p, then you multiply p x times, and n minus x must be going into the second group with probability 1 minus p. And so you multiply 1 minus p, n minus x times. So that's where you get the expression for the binomial distribution. And now multinomial coefficients are quite similar to binomial coefficients when you understand them as dividing up n objects into two groups. But now we're dividing n objects into k groups. And so we have k different sizes for those groups, where these sizes have to add up to n. Right? And then the expression for this is n factorial over the factorial of each of the sizes of the groups. And so it's just like the multinomial coefficients, but instead of just x and n minus x, you have x1, x2, x3, up to xk. And it's just because you're dividing the n factorial by the ways of ordering all of the k groups. So I hope that makes sense. And then the multinomial distribution is the probability of dividing n objects into k groups with sizes x sub 1 up to x sub k, where these sizes, of course, have to add up to n. And that each of the classifications is independent with probabilities p1 to pk corresponding to each of those groups, where p1 to pk have to add up to 1. And this is the expression for this any of these collection of sizes of the groups. So you've got the number of ways of dividing up the n objects into groups of those sizes. And then you have the probability for each of those ways of dividing them up. And again, you're just, because the classifications are independent, you're just multiplying the corresponding probability by the number of times that you've classified an object into that corresponding group. So you have p sub 1 to the power of x sub 1 all the way up to p sub k to the power of x sub k. Okay, so how does this apply to closed population capture-recapture? Well, first let's talk about this Schnabel census data. So we have all of our observed capture histories, and we're going to count how many of each type of capture history there are. So, for example, if there were 2 surveys, which would be the Lincoln-Peterson method from lecture 1, the possible capture histories would be 0, 0, meaning you didn't capture the animal ever, 1, 0, meaning you caught it on the first occasion but not on the second, 1, 1, and 0, 1. And those are all the possibilities. So if the observed capture histories are 10, 11, 01, 01, which is a very tiny data set, right? Then we would just count that there's 1 of 10 and 1 of 11 and 2 of 01. And that's the Schnabel census for this set of data. And then our notation will be that the count for a particular capture history W is A sub W, and and the total number observed is R. So of course, this capture history 00 is never actually observed because you never caught the animal. And the number of those, A sub 00, equals the population size minus the total number of animals you actually observed. That's what we want to estimate. Right? So capture history probabilities. You calculate the capture history probabilities in terms of the capture probabilities, which, remember, these are expressed differently depending on the type of model. But if we were using model MT, then we would have a different capture probability for each survey. So we've got 2 surveys. So we'll have P sub 1 and P sub 2. And then the capture probability, for example, for 1.0 would just be P sub 1 times 1 minus P sub 2, because you didn't catch the animal on the second occasion. And we call the capture, the probability of a capture history P sub W for any capture history W. And we'll call the probability of not observing an animal Q, capital Q, and in this example, capital Q is 1 minus P1 times 1 minus P2, because you never captured the animal. Okay, so now we can express the probability of the Schnabel census, which, remember, is the number of each kind of capture history that we've observed, using this multinomial distribution. So you have the n animals in the population, and you're dividing them into groups by their capture histories. So the sizes of the sizes of the groups are the number of each capture history that you've observed, and there's also the number of animals that are not observed. So that's the remaining n minus r. So, and of course there are independent classifications, and the corresponding probabilities are the capture history probabilities that we've calculated. So this is the multinomial distribution. The number of objects that we're dividing up is the whole population, capital N. And then the sizes of the groups are the numbers of each type of capture history that we've observed, and also the number that we never observed. And so we don't know capital N, but so capital N is the parameter here, one of the parameters. And so we have Q here for the probability of an animal not being observed. And so we're exponentiating it by n minus r times, because that's how many animals we don't observe. And then we have the capture history probability for each type of capture history, and it's exponentiated by the count corresponding to that capture history. And we've got that for every type of capture history. So this is ingenious, right? We're including the number of unobserved animals in a probability distribution with the observed. And that's really the essence of capture-recapture. That's how it works. That kind of creativity seems to be one of the main attractions of statistical ecology generally, along with working with biologists and studying cool animals. So this distribution is also called the likelihood given to the population size and capture probabilities by the capture history counts. So these are our data, and these are our parameters. So the data is giving a likelihood to any particular value of the parameters. which you express that in this way. So you have L for likelihood, and then your parameters, and then a semicolon, and then your data. And it's just the same probability distribution above, but now you're considering it as a function of the parameters. And so, oh yeah, and this S here is the number of surveys. So you have one capture probability for every survey. And so we want to find the maximum likelihood estimates, which are the values of the parameters that give the highest probability for the observed data. So we have this function for the probability, and we want to find the parameter values that maximize this function. And we'll use those for our estimates. For 2 or 3 surveys, there are analytic expressions for those parameter values that give that maximum. But in general, we'll usually use numerical optimization. And I'll talk about that more later. So we've been using this set of counts, the number of each capture history, the number observed of each capture history. And if we think about the capture histories themselves, for any set of counts, A sub W, which add up to R is the total number of animals observed, there are R factorial divided by the product of A sub W factorials for all of the different W. That's the number of ways of dividing the R capture histories into groups of those sizes. So that's just the multinomial coefficient for dividing R objects into groups of size A sub W. So if we want to find the probability of the set of capture histories, including the number of capture histories, instead of just the probability of the counts, then we have to divide those count probabilities by this number of ways that we can get a set of capture histories that correspond to those counts. And so if you divide this expression by the number of ways, then this part of the denominator disappears, and it's replaced with this factorial here. And so now we have the probability of the capture histories themselves, plus the number of capture histories. And I've changed the notation a bit here. I think I'm explaining that in the next slide. But theta is now the set of capture probabilities. And I think I should also have n here as well, because n is the other parameter. And I'm also replaced p sub w with p of xi. So xi is one of our capture histories. And so this is the probability of all of the capture histories. And then over here, p sub w has been replaced with p sub I. And we're multiplying all of the capture histories. Although I should have changed this. This should be R here. We're gonna change notation in the next slide. I think I've done it too soon. So the number of capture histories R is also part of the data. It's implied by the values of the counts of the capture histories, but not by the values of the capture histories themselves. So that's why we have to include it here. Okay, so here's the change in notation that we're doing. So small n equals R, that's the number of capture histories in total, the number of animals that we've observed. K equals S, the number of surveys. So now theta is the capture probabilities, and now it's from P sub 1 to P sub k. And P sub theta is 1 minus Q. So Q was the probability of not observing an animal. The 1 minus Q is the probability of observing it at least once, right? I'm going to say the probability that an animal is observed. And we're also going to make the dependence on the capture probabilities theta explicit. So now we get the likelihood, which is given on page 4 of Rachel's notes. So this is just the expression on the previous slide, but now we're writing it in terms of a likelihood instead of a probability distribution. And so we've just changed the notation. So we've got n for r, and 1 minus P sub theta for Q. And we're making this dependence on the capture probabilities explicit here. So the capture history probabilities depend on the parameters, which are the capture probabilities. So all we're doing here is changing notation, and we're now using this expression is derived from the probability of the capture histories rather than the Schnabel census, which is the counts of the capture histories. So you can see that in terms of the parameters of interest, that is our population size and capture probabilities, this is actually just the same as the Schnabel census likelihood, and it'll produce the same MLEs. It's just a different way of writing the same likelihood. And you can also write it by taking out a factor of P sub theta for each of the capture history probabilities. And if you put it here, then this part of the likelihood is now the binomial distribution of the number of animals that are observed out of the population and the number that are not observed. And so this formulation of the likelihood is called the binomial detectability likelihood, where it's partitioned into the probability of detecting the number of animals that we did detect and not detecting the number of animals that we did not detect. And then here we have the conditional probability of the capture histories given that the animal was detected. And of course, the conditional probabilities of the unobserved capture histories, given that they are unobserved, are all 1, because there's only one unobserved capture history, which is the 0, 0 capture history. Okay, so this is actually a non-regular likelihood, which means that n is constraining the possible number, little n, of capture histories. So the small n can never be larger than big N, because you can never capture more animals than exist in the population, right? And when your parameter constrains your data, you don't have a regular likelihood. Also, small n and x sub I have different distributions. So the distribution of small n is in the first part of the likelihood, and then the distribution for the capture histories is in the second part. So they have different distributions, which means also means it's not a regular likelihood. And also x sub I are not drawn from the overall multinomial distribution. You might be confused if you thought that x sub I are just coming from this multinomial, but they're not, because you can never observe the 0, 0 capture history. So yeah, so don't be confused by that. These are not just being drawn from a standard multinomial. This leads to the maximum likelihood estimate for n actually being asymptotically log normally distributed. So in general, when we if we have a regular likelihood, we can say that the parameter estimates, the maximum likelihood estimates, will be asymptotically normally distributed, which is how we get our normal confidence intervals. But because of this non-regularity, Rachel Fuster and another academic, Jupe, have shown that this distribution for n is actually log normal. What that means is that the confidence intervals will be skewed to the right. So the lower bound will be closer to the estimate and the upper bound will be further away. But it actually doesn't seem to make much difference from, apparently, from simulation studies. Okay, so that's quite a lot for this first section. I'll probably leave it here for now. And then in the next section of this lecture, in the next clip, we'll start having a look at open population capture-recapture data. So I'll see you then.